The audio version of this page was provided by CesarUSA.com. You can pause the video to read and understand the code. The original document can be read and printed from https://docs.modular.com/mojo/programming-manual.html. The Mojo Programming Manual. Mojo is a programming language that is as easy to use as Python but with the performance of C++ and Rust. Furthermore, Mojo provides the ability to leverage the entire Python library ecosystem. Mojo achieves this feat by utilizing next-generation compiler technologies with integrated caching, multi-threading, and cloud distribution technologies. Furthermore, Mojo's auto-tuning and compile-time metaprogramming features allow you to write code that is portable to even the most exotic hardware. More importantly, Mojo allows you to leverage the entire Python ecosystem so you can continue to use tools you are familiar with. Mojo is designed to become a superset of Python over time by preserving Python's dynamic features while adding new primitives for systems programming. These new system programming primitives will allow Mojo developers to build high-performance libraries that currently require C, C++, Rust, CUDA, and other accelerator systems. By bringing together the best of dynamic languages and systems languages, we hope to provide a unified programming model that works across levels of abstraction, is friendly for novice programmers, and scales across many use cases from accelerators through to application programming and scripting. This document is an introduction to the Mojo programming language, fit for consumption by Mojo programmers. It assumes knowledge of Python and systems programming concepts, but it does not expect the reader to be a compiler nerd. At the moment, Mojo is still a work in progress and the documentation is targeted to developers with systems programming experience. As the language grows and becomes more broadly available, we intend for it to be friendly and accessible to everyone, including beginner programmers. It's just not there today. Using the Mojo compiler, you can run a Mojo program from a terminal just like you can with Python. So if you have a file named hello, Mojo, or hello, fire, yes, the file extension can be an emoji. Just type Mojo hello, Mojo. Again, you can use either the emoji or the Mojo suffix. If you are interested in diving into the internal implementation details of Mojo, it can be instructive to look at types in the standard library, example code in notebooks, blogs, and other sample code. Basic systems programming extensions. Given our goal of compatibility and Python's strength with high-level applications and dynamic APIs, we don't have to spend much time explaining how those portions of the language work. On the other hand, Python's support for systems programming is mainly delegated to C, and we want to provide a single system that is great in that world. As such, this section breaks down each major component and feature and describes how to use them with examples. Let and var declarations inside a def in Mojo. You may assign a value to a name and it implicitly creates a function scope variable just like in Python. This provides a very dynamic and low-ceremony way to write code, but it is a challenge for two reasons. Systems programmers often want to declare that a value is immutable for type safety and performance. They may want to get an error if they mistype a variable name in an assignment. To support this, Mojo provides scoped runtime value declarations. Let is immutable, and var is mutable. These values use lexical scoping and support name shadowing. Let and var declarations support type specifiers as well as patterns, and late initialization. Note that let and var are completely opt-in when in def declarations. You can still use implicitly declared values as with Python, and they get function scope as usual. Struct types Mojo is based on MLIR and LLVM, which offer a cutting-edge compiler and code generation system used in many programming languages. This lets us have better control over data organization, direct access to data fields, and other ways to improve performance. An important feature of modern systems programming languages is the ability to build high-level and safe abstractions on top of these complex, low-level operations without any performance loss. In Mojo, this is provided by the struct type. A struct in Mojo is similar to a Python class. They both support methods, fields, operator overloading, decorators for metaprogramming, etc. Their differences are as follows. Python classes are dynamic. They allow for dynamic dispatch, monkey patching, or swizzling, and dynamically binding instance properties at runtime. Mojo structs are static. They are bound at compile time. You cannot add methods at runtime. Structs allow you to trade flexibility for performance while being safe and easy to use. Here's a simple definition of a struct. Syntactically, the biggest difference compared to a Python class is that all instance properties in a struct must be explicitly declared with a var or let declaration. In Mojo, the structure and contents of a struct are set in advance and can't be changed while the program is running. Unlike in Python, where you can add, remove, or change attributes of an object on the fly, Mojo doesn't allow that for structs. This means you can't use del to remove a method or change its value in the middle of running the program. However, the static nature of struct has some great benefits. It helps Mojo run your code faster. The program knows exactly where to find the struct's information and how to use it without any extra steps or delays. Mojo's structs also work really well with features you might already know from Python, like operator overloading, which lets you change how math symbols like plus and minus work with your own data. Furthermore, all the standard types, like int, bool, string, and even tuple, are made using structs. This means they're part of the standard set of tools you can use, rather than being hardwired into the language itself. This gives you more flexibility and control when writing your code. If you're wondering what the inout means on the self argument, this indicates that the argument is mutable and changes made inside the function are visible to the caller. For details, see below about inout arguments. Int versus int. In Mojo, you might notice that we use int with a capital I, which is different from Python's int with a lowercase I. This difference is on purpose, and it's actually a good thing. In Python, the int type can handle really big numbers and has some extra features, like checking if two numbers are the same object. But this comes with some extra baggage that can slow things down. Mojo's int is different. It's designed to be simple, fast, and tuned for your computer's hardware to handle quickly. We made this choice for two main reasons. We want to give programmers who need to work closely with computer hardware, systems programmers, a transparent and reliable way to interact with hardware. We don't want to rely on fancy tricks, like JIT compilers, to make things faster. We want Mojo to work well with Python without causing any issues. By using a different name, int instead of int, we can keep both types in Mojo without changing how Python's int works. As a bonus, int follows the same naming style as other custom data types you might create in Mojo. Additionally, int is a struct that's included in Mojo's standard set of tools. Strong type checking. Even though you can still use flexible types like in Python, Mojo lets you use strict type checking. Type checking can make your code more predictable, manageable, and secure. One of the primary ways to employ strong type checking is with Mojo's struct type. A struct definition in Mojo defines a compile time-bound name, and references to that name in a type context are treated as a strong specification for the value being defined. For example, consider the following code that uses the myPair struct shown above. When you run this code, you'll get a compile time error telling you that 4 cannot be converted to myPair, which is what the RHS of myPair __LT__ requires. This is a familiar experience when working with systems programming languages, but it's not how Python works. Python has syntactically identical features for myPy type annotations, but they are not enforced by the compiler. Instead, they are hints that inform static analysis. By tying types to specific declarations, Mojo can handle both the classical type annotation hints and strong type specifications without breaking compatibility. Type checking isn't the only use case for strong types. Since we know the types are accurate, we can optimize the code based on those types, pass values in registers, and be as efficient as C for argument passing and other low-level details. This is the foundation of the safety and predictability guarantees Mojo provides to systems programmers. Overloaded functions and methods. Like Python, you can define functions in Mojo without specifying argument data types, and Mojo will handle them dynamically. This is nice when you want expressive APIs that just work by accepting arbitrary inputs and let dynamic dispatch decide how to handle the data. However, when you want to ensure type safety, as discussed above, Mojo also offers full support for overloaded functions and methods. This allows you to define multiple functions with the same name but with different arguments. This is a common feature seen in many languages, such as C++, Java, and Swift. When resolving a function call, Mojo tries each candidate and uses the one that works, if only one works. Or it picks the closest match, if it can determine a close match, or it reports that the call is ambiguous if it can't figure out which one to pick. In the latter case, you can resolve the ambiguity by adding an explicit cast on the call site. Let's look at an example. You can overload methods in structs and classes and overload module-level functions. Mojo doesn't support overloading solely on result type, and doesn't use result type or contextual type information for type inference, keeping things simple, fast, and predictable. Mojo will never produce an expression too complex error, because its type checker is simple and fast by definition. Again, if you leave your argument names without type definitions, then the function behaves just like Python with dynamic types. As soon as you define a single argument type, Mojo will look for overload candidates and resolve function calls as described above. FN definitions. The extensions above are the cornerstone that provides low-level programming and provide abstraction capabilities. But many systems programmers prefer more control and predictability than what def in Mojo provides. To recap, def is defined by necessity to be very dynamic, flexible, and generally compatible with Python. Arguments are mutable, local variables are implicitly declared on first use, and scoping isn't enforced. This is great for high-level programming and scripting, but is not always great for systems programming. To complement this, Mojo provides an FN declaration which is like a strict mode for def. Alternative, instead of using a new keyword like FN, we could instead add a modifier or decorator like at strict def. However, we need to take new keywords anyway, and there is little cost to doing so. Also, in practice in systems programming domains, FN is used all the time, so it probably makes sense to make it first class. As far as a caller is concerned, fn and def are interchangeable. There is nothing a def can provide that a fn cannot, and vice versa. The difference is that a fn is more limited and controlled on the inside of its body, alternatively, pedantic and strict. Specifically, FNs have a number of limitations compared to def functions. Argument values default to being immutable in the body of the function, like a let, instead of mutable, like a var. This catches accidental mutations and permits the use of non-copyable types as arguments. Argument values require a type specification, except for self in a method, catching accidental omission of type specifications. Similarly, a missing return type specifier is interpreted as returning none instead of an unknown return type. Note that both can be explicitly declared to return object, which allows one to opt in to the behavior of a def if desired. Implicit declaration of local variables is disabled, so all locals must be declared. This catches name typos and dovetails with the scoping provided by let and var. Both support raising exceptions, but this must be explicitly declared on a fn with the raises keyword. Programming patterns will vary widely across teams, and this level of strictness will not be for everyone. We expect that folks who are used to C++ and already use my py style type annotations in Python to prefer the use of FNS, but higher-level programmers and ML researchers to continue to use def. Mojo allows you to freely intermix def and fn declarations, e.g. implementing some methods with one and others with the other, and allows each team or programmer to decide what is best for their use case. For more about argument behavior in Mojo functions, see the section below about argument passing control and memory ownership. The ___ copy init ___ and ___ move init ___ special methods. Mojo supports full value semantics as seen in languages like C++ and Swift. And it makes defining simple aggregates of fields very easy with its @value decorator, described in more detail below. For advanced use cases, Mojo allows you to define custom constructors, using Python's existing ___ special method. Custom destructors, using the existing __del__ special method, and custom copy and move constructors using the new ___ copy init ___ and ___ move init ___ special methods. These low-level customization hooks can be useful when doing low-level systems programming, e.g. with manual memory management. For example, consider a dynamic string type that needs to allocate memory for the string data when constructed and destroy it when the value is destroyed. This myString type is implemented using low-level functions to show a simple example of how this works. A more realistic implementation would use short string optimizations, etc. However, if you go ahead and try this out, you might be surprised. The Mojo compiler doesn't allow us to copy the string from A to B because it doesn't know how to. myString contains an instance of pointer, which is equivalent to a low-level C pointer, and Mojo doesn't know what kind of data it points to or how to copy it. More generally, some types, like atomic numbers, cannot be copied or moved around because their address provides an identity just like a class instance does. In this case, we do want our string to be copyable. To enable this, we implement the ___ copy init ___ special method, which is conventionally implemented like this. With this implementation, our code above works correctly, and the B equals a copy produces a logically distinct instance of the string with its own lifetime and data. The copy is made with the C-style stirred-up function as instructed by the lines of code above. Mojo also supports the ___ move init ___ method. which allows both Rust style moves, which take a value when a lifetime ends, and C++ style moves, where the contents of a value are removed. But the destructor still runs, and allows defining custom move logic. For more discussion about value lifetimes, see the value lifecycle section below. Mojo provides full control over the lifetime of a value, including the ability to make types copyable, move only, and not movable. This is more control than languages like Swift and Rust offer, which require values to at least be movable. If you are curious how existing can be passed into the __copyInit__ method without itself creating a copy, check out the section on borrowed arguments below. Argument passing control and memory ownership. In both Python and Mojo, much of the language revolves around function calls. A lot of the, apparently, built-in behaviors are implemented in the standard library with __ methods. Inside these magic functions is where a lot of memory ownership is determined through argument passing. Let's review some details about how Python and Mojo pass arguments. All values passed into a Python def function use reference semantics. This means the function can modify mutable objects passed into it, and those changes are visible outside the function. However, the behavior is sometimes surprising for the uninitiated, because you can change the object that an argument points to, and that change is not visible outside the function. All values passed into a Mojo def function use value semantics by default. Compared to Python, this is an important difference. A Mojo def function receives a copy of all arguments. It can modify arguments inside the function, but the changes are not visible outside the function. All values passed into a Mojo fn function are immutable references by default. This means the function can read the original object. It is not a copy, but it cannot modify the object at all. This convention for immutable argument passing in a Mojo fn is called borrowing. In the following sections, we'll explain how you can change the argument passing behavior in Mojo for both def and fn functions. Why argument conventions are important. In Python, all fundamental values are references to objects. As described above, a Python function can modify the original object. Thus, Python developers are used to thinking about everything as reference semantic. However, at the CPython or machine level, you can see that the references themselves are actually passed by copy. Python copies a pointer and adjusts reference counts. This Python approach provides a comfortable programming model for most people, but it requires all values to be heap allocated, and results are occasionally surprising results due to reference sharing. Mojo classes, TODO, will follow the same reference semantic approach for most objects, but this isn't practical for simple types like integers in a systems programming context. In these scenarios, we want the values to live on the stack or even in hardware registers. As such, Mojo structs are always inlined into their container, whether that be as the field of another type or into the stack frame of the containing function. This raises some interesting questions. How do you implement methods that need to mutate self of a structure type, such as __IADD__? How does let work, and how does it prevent mutation? How are the lifetimes of these values controlled to keep Mojo a memory-safe language? The answer is that the Mojo compiler uses dataflow analysis and type annotations to provide full control over value copies, aliasing of references, and mutation control. These features are similar in many ways to features in the Rust language, but they work somewhat differently in order to make Mojo easier to learn. And they integrate better into the Python ecosystem without requiring a massive annotation burden. In the following sections, you'll learn about how you can control memory ownership for objects passed into Mojo fn functions. Immutable arguments, borrowed. A borrowed object is an immutable reference to an object that a function receives, instead of receiving a copy of the object. So the callee function has full read and execute access to the object, but it cannot modify it. The caller still has exclusive ownership of the object. Although this is the default behavior for fn arguments, you can explicitly define it with the borrowed keyword if you'd like. You can also apply borrowed to def arguments. This default applies to all arguments uniformly, including the self-argument of methods. This is much more efficient when passing large values or when passing expensive values like a reference counted pointer, which is the default for Python, Mojo classes. Because the copy constructor and destructor don't have to be invoked when passing the argument. Here is a more elaborate example building on the code above. Because the default argument convention for fn functions is borrowed, Mojo has simple and logical code that does the right thing by default. For example, we don't want to copy or move all of something big just to invoke the print_id method, or when calling use_something_big. This borrowed argument convention is similar in some ways to passing an argument by const and in C++, which avoids a copy of the value and disables mutability in the callee. However, the borrowed convention differs from const and in C++ in two important ways. The Mojo compiler implements a borrow checker, similar to Rust, that prevents code from dynamically forming mutable references to a value when there are immutable references outstanding. And it prevents multiple mutable references to the same value. You are allowed to have multiple borrows, as the call to use _something_big does above, but you cannot pass something by mutable reference and borrow at the same time. TODO. Not currently enabled. Small values like int, float, and SIMD are passed directly in machine registers instead of through an extra indirection. This is because they are declared with the @register_passable decorator. This is a significant performance enhancement when compared to languages like C++ and Rust, and moves this optimization from every call site to being declarative on a type. Similar to Rust, Mojo's borrow checker enforces the exclusivity of invariants. The major difference between Rust and Mojo is that Mojo does not require a sigil on the caller side to pass by borrow. Also, Mojo is more efficient when passing small values, and Rust defaults to moving values instead of passing them around by borrow. These policy and syntax decisions allow Mojo to provide an easier-to-use programming model. Mutable arguments, in-out. On the other hand, if you define an fn function and want an argument to be mutable, so that changes to the argument inside the function are visible outside the function, you must declare the argument as mutable with the in-out keyword. Consider the following example, in which the __IADD__ function tries to modify self. The problem here is that self is immutable because this is a Mojo fn function, so it can't change the internal state of the argument. The solution is to declare that the argument is mutable by adding the in-out keyword on the self-argument name. Tip: when you see in-out, it means that any changes made to the argument inside the function are visible outside the function. Now the self-argument is mutable in the function and any changes are visible in the caller, even if the caller has a non-trivial computation to access it, like an array subscript. Mojo implements the in-place mutation of the above inline fixed vector element by emitting a call to __getItem__ into a temporary buffer, followed by a store with __setItem__ after the call. Mutation of the let value fails because it isn't possible to form a mutable reference to an immutable value. Similarly, the compiler rejects attempts to use a subscript with an inout argument if it implements __getItem__, but not __setItem__. Of course, you can declare multiple inout arguments. For example, you can define and use a swap function like this. A very important aspect of this system is that it all composes correctly. Notice that we don't call this argument passing by reference. Although the inout convention is conceptually the same, we don't call it by reference passing because the implementation may actually pass values using pointers. Transfer arguments, owned and caret. The final argument convention that Mojo supports is the owned argument convention. This convention is used for functions that want to take exclusive ownership over a value, and it is often used with the postfixed caret operator. For example, imagine you're working with a move-only type like a unique pointer. While the borrow convention makes it easy to work with the unique pointer without ceremony, at some point you might want to transfer ownership to some other function. This is what the caret transfer operator does. For movable types, the caret operator ends the lifetime of a value binding and transfers the value ownership to something else, in this case, the take_ptr function. To support this, you can define functions as taking owned arguments. For example, you define take_ptr, like so. Because it is declared owned, the take_ptr function knows it has unique access to the value. This is very important for things like unique pointers, and it's useful when you want to avoid copies. For example, you will notably see the owned convention on destructors and on consuming move constructor. For example, our myString type from earlier can be defined as follows. Specifying owned in the __del__ function is important because you must own a value to destroy it. Comparing def and fn argument passing. Mojo's def function is essentially just sugaring for the fn function. A def argument without an explicit type annotation defaults to object. A def argument without a convention keyword, such as inout or owned, is passed by implicit copy into a mutable var with the same name as the argument. This requires that the type have a __copyInit___ method. For example, these two functions have the same behavior. The shadow copies typically add no overhead, because references for small types like object are cheap to copy. The expensive part is adjusting the reference count. But that's eliminated by a move optimization. Python integration. It's easy to use Python modules you know and love in Mojo. You can import any Python module into your Mojo program and create Python types from Mojo types. Importing Python modules. To import a Python module in Mojo, just call Python import_module with the module name. Yes, this imports Python NumPy, and you can import any other Python module. However, remember that you're working with a Python object, so some Mojo functions like print won't work. If you want to print a Python type in Mojo, you need to use Python's built-in print function. Currently, you cannot import individual members, such as a single Python class or function. You must import the whole Python module and then access members through the module name. Importing local Python modules. If you have some local Python code you want to use in Mojo, just add the directory to the Python path and then import the module. For example, suppose you have a Python file like this. Here's how you can import it and use it in Mojo. Here's how you can import it and use it in Mojo. There's no need to worry about memory management when using Python in Mojo. Everything just works because Mojo was designed for Python from the beginning. Mojo types in Python. Mojo primitive types implicitly convert into Python objects. Today we support lists, tuples, integers, floats, booleans, and strings. For example, given this Python function that prints Python types, you can import it and pass it Mojo types, no problem. It will output the types after implicit conversion to Python types. Mojo doesn't have a standard dictionary yet, so it is not yet possible to create a Python dictionary from a Mojo dictionary. You can work with Python dictionaries in Mojo though. Parameterization. Compile time metaprogramming. One of Python's most amazing features is its extensible runtime metaprogramming features. This has enabled a wide range of libraries and provides a flexible and extensible programming model that Python programmers everywhere benefit from. Unfortunately, these features also come at a cost. Because they are evaluated at runtime, they directly impact runtime efficiency of the underlying code. Because they are not known to the IDE, it is difficult for IDE features like code completion to understand them and use them to improve the developer experience. Outside the Python ecosystem, static metaprogramming is also an important part of development, enabling the development of new programming paradigms and advanced libraries. There are many examples of prior art in this space, with different trade-offs. For example, 1. Preprocessors, e.g. C preprocessor, Lex, YACC, etc., are perhaps the heaviest-handed. They are fully general but the worst in terms of developer experience and tools integration. 2. Some languages, like Lisp and Rust, support, sometimes, hygienic, macro expansion features, enabling syntactic extension and boilerplate reduction with somewhat better tooling integration. 3. Some older languages like C++ have very large and complex metaprogramming languages, templates, that are a dual to the runtime language. These are notably difficult to learn and have poor compile times and error messages. 4. Some languages, like Swift, build many features into the core language in a first-class way to provide good ergonomics for common cases at the expense of generality. 5. Some newer languages like Zig integrate a language interpreter into the compilation flow, and allow the interpreter to reflect over the AST as it is compiled. This allows many of the same features as a macro system with better extensibility and generality. For modulars work in AI, high-performance machine learning kernels, and accelerators, we need high abstraction capabilities provided by advanced metaprogramming systems. We needed high-level zero-cost abstractions, expressive libraries, and large-scale integration of multiple variants of algorithms. We want library developers to be able to extend the system, just like they do in Python, providing an extensible developer platform. That said, we are not willing to sacrifice developer experience, including compile times and error messages, nor are we interested in building a parallel language ecosystem that is difficult to teach. We can learn from these previous systems but also have new technologies to build on top of, including MLIR and fine-grained language integrated caching technologies. As such, Mojo supports compile time metaprogramming built into the compiler as a separate stage of compilation, after parsing, semantic analysis, and IR generation, but before lowering to target specific code. It uses the same host language for runtime programs as it does for metaprograms, and leverages MLIR to represent and evaluate these programs predictably. Let's take a look at some simple examples. About parameters. Python developers use the words arguments and parameters fairly interchangeably for things that are passed into functions. We decided to reclaim parameter and parameter expression to represent a compile time value in Mojo, and continue to use argument and expression to refer to runtime values. This allows us to align around words like parameterized and parametric for compile time metaprogramming. Defining parameterized types and functions. Mojo structs and functions may each be parameterized, but an example can help motivate why we care. Let's look at a SIMD type, which represents a low-level vector register in hardware that holds multiple instances of a scalar data type. Hardware accelerators these days are getting exotic data types, and it isn't uncommon to work with CPUs that have 512-bit or longer SIMD vectors. There is a lot of diversity in hardware, including many brands like SSE, AVX512, Neon, SVE, RVV, etc., but many operations are common and used by numerics and ML kernel developers. The SIMD type exposes them to Mojo programmers. Here is a cut-down version of the SIMD API in the Mojo standard library. Parameters in Mojo are declared in square brackets using an extended version of the PEP 695 syntax. They are named and have types like normal values in a Mojo program, but they are evaluated at compile time instead of runtime by the target program. The runtime program may use the value of parameters, because the parameters are resolved at compile time before they are needed by the runtime program, but the compile time parameter expressions may not use runtime values. In the case of the SIMD excerpt above, there are three declared parameters. The SIMD struct is parameterized by a type parameter and a size parameter. The cast method is further parameterized with a target parameter. Because SIMD is a parameterized type, the type of a self-argument carries the parameters. The full type name is SIMD, type, size. While it is always valid to write this out, as shown in the return type of splat, this can be verbose, so we recommend using the self type, from PEP 673, like the __add _ example does. Using parameterized types and functions. For the SIMD type, size specifies the number of elements in a SIMD vector, and type specifies the element type. For example, you might use a 4x float to represent a small floating point vector or a 32x bfloat 16 inches on an AVX512 system with the bfloat 16 inches machine learning type. Correction by the voice translator. Not inches, it is just an ending quotation mark. Note that the cast method needs an additional parameter to indicate what type to cast to. That is handled by parameterizing the call to cast. The example above shows the use of concrete types. But the major power of parameters comes from the ability to define parametric algorithms and types. For example, it's quite easy to define parametric algorithms, such as those that are length and d-type agnostic. The Mojo compiler is fairly smart about type inference with parameters. Note that this function is able to call the parametric sqrt function without specifying the parameters. The compiler infers its parameters as if you wrote sqrt, width, type, x, explicitly. Also note that RSQRT chose to define its first parameter named width, but the SIMD type names its size without challenge. Parameter expressions are just Mojo code. All parameters and parameter expressions are typed using the same type system as the runtime program. Int and dtype are implemented in the Mojo standard library as structs. Parameters are quite powerful, supporting the use of expressions with operators, function calls at compile time, and more, just like a runtime program. This enables the use of many dependent type features. For example, you might want to define a helper function to concatenate two SIMD vectors. Note how the resulting length is the sum of the input vector lengths, and you can express that with a simple plus operation. For a more complex example, take a look at the SIMD shuffle method in the standard library. It takes two input SIMD values, a vector shuffle mask as a list, and returns a SIMD that matches the length of the shuffle mask. Powerful compile time programming. While simple expressions are useful, sometimes you want to write imperative compile time logic with control flow. For example, the isClose function in the Mojo Math module uses exact equality for integers but close comparison for floating point. You can even do compile time recursion. For instance, here is an example tree reduction algorithm that sums all elements of a vector recursively into a scalar. This makes use of the itParameter if feature, which is an if statement that runs at compile time. It requires that its condition be a valid parameter expression, and ensures that only the live branch of the if statement is compiled into the program. Mojo types are just parameter expressions. While we've shown how you can use parameter expressions within types, in both Python and Mojo, type annotations can themselves be arbitrary expressions. Types in Mojo have a special metatype type, allowing type parametric algorithms and functions to be defined. For example, you can define an algorithm like the C++ std vector class like this. Notice that the type parameter is used as the formal type for the value arguments and the return type of the __getItem___ function. Parameters allow the dynamic vector type to provide different APIs based on the different use cases. There are many other cases that benefit from more advanced use cases. For example, the parallel processing library defines the parallel for each an algorithm, which executes a closure n times in parallel, feeding in a value from the context. That value can be of any type. This is possible because the func parameter is allowed to refer to the earlier arg_type parameter, and that refines its type in turn. Another example where this is important is with variadic generics, where an algorithm or data structure may need to be defined over a list of heterogeneous types. Note, we don't have enough metatype helpers in place yet, but we should be able to write something like this in the future, though overloading is still a better way to handle this. Alias, named parameter expressions. It is very common to want to name compile time values. Whereas var defines a runtime value, and let defines a runtime constant. We need a way to define a compile time temporary value. For this, Mojo uses an alias declaration. For example, the dtype struct implements a simple enum using aliases for the enumerators like this. The actual internal implementation details vary a bit. This allows clients to use dtype f32 as a parameter expression, which also works as a runtime value, naturally. Note that this is invoking the runtime constructor for dtype at compile time. Types are another common use for alias. Because types are compile time expressions, it is handy to be able to do things like this. Like var and let, aliases obey scope, and you can use local aliases within functions as you'd expect. Auto-tuning, adaptive compilation. Mojo parameter expressions allow you to write portable parametric algorithms like you can do in other languages. But when writing high-performance code, you still have to pick concrete values to use for the parameters. For example, when writing high-performance numeric algorithms, you might want to use memory tiling to accelerate the algorithm, but the dimensions to use depend highly on the available hardware features, the sizes of the cache, what gets fused into the kernel, and many other fiddly details. Even vector length can be difficult to manage, because the vector length of a typical machine depends on the datatype. And some datatypes like bfloat16 don't have full support on all implementations. Mojo helps by providing an autotune function in the standard library. For example, if you want to write a vector length agnostic algorithm to a buffer of data, you might write it like this. When compiling instantiations of this code, Mojo forks compilation of this algorithm and decides which value to use by measuring what works best in practice for the target hardware. It evaluates the different values of the vector_len expression and picks the fastest one according to a user-defined performance evaluator. Because it measures and evaluates each option individually, it might pick a different vector length for F32 than for SI8, for example. This simple feature is pretty powerful, going beyond simple integer constants, because functions and types are also parameter expressions. Users can instrument the search of xb_buffer_impl by providing a performance evaluator and using the search standard library function. Search takes an evaluator and a forked function and returns the fastest implementation selected by the evaluator as a parameter result. In this example, we provided express_evaluator to the search function as the performance evaluator. Performance evaluators are invoked with a list of candidate functions and should return the index of the best one. Mojo's standard library provides a benchmark module that you can use to time functions. Autotuning has an exponential runtime. It benefits from internal implementation details of the Mojo compiler stack, particularly MLIR, integrated caching, and distribution of compilation. This is a power user feature and needs continued development and iteration over time. Value lifecycle, birth, life and death of a value. Now that we have an understanding of the different ingredients that can go into building functions and the types system, we can look at how to put them together to model important types that you may want to express in Mojo. Many existing languages express design points with different trade-offs. C++, for example, is very powerful but often accused of getting the defaults wrong, which leads to bugs and misfeatures. Swift is easy to work with, but has a less predictable model that copies values a lot and is dependent on an arc optimizer for performance. Rust started with strong value ownership goals to satisfy its borrow checker, but relies on values being movable, which makes it challenging to express custom move constructors and can put a lot of stress on mimicp performance. In Python, everything is a reference to a class, so it never really faces issues with types. For Mojo, we benefit from learning from these existing systems, and aim to provide a model that is very powerful while still easy to learn and understand. We also don't want to require best effort and difficult to predict optimization passes built into a sufficiently smart compiler. To explore these issues, we look at different value classifications and the relevant Mojo features that go into expressing them, and build from the bottom up. We use C++ as the primary comparison point in examples because it is widely known, but we occasionally reference other languages if they provide a better comparison point. Types that cannot be instantiated. The most bare-bones type in Mojo is one that doesn't allow you to create instances of it. These types have no initializer at all, and if they have a destructor, it will never be invoked, because there cannot be instances to destroy. Mojo types do not get default constructors, move constructors, member-wise initializers or anything else by default, so it is impossible to create an instance of this no-instances type. In order to get them, you need to define an __init__ method or use a decorator that synthesizes an initializer. As shown, these types can be useful as namespaces because you can refer to static members like noinstances.my_int or noinstances.print_hello, even though you cannot instantiate an instance of the type. Non-movable and non-copyable types. If we take a step up the ladder of sophistication, we'll get to types that can be instantiated, but once they are pinned to an address in memory, they cannot be implicitly moved or copied. This can be useful to implement types like atomic operations, such as std, atomic in C++, or other types where the memory address of the value is its identity and is critical to its purpose. This class defines an initializer but no copy or move constructors, so once it is initialized it can never be moved or copied. This is safe and useful because Mojo's ownership system is fully address correct. When this is initialized onto the stack or in the field of some other type, it never needs to move. Note that Mojo's approach controls only the built-in move operations, such as a=b copies and the transfer operator. One useful pattern you can use for your own types, like atomic above, is to add an explicit copy method, a non-dunder method. This can be useful to make explicit copies of an instance when it is known safe to the programmer. Unique move only types. If we take one more step up the ladder of capabilities, we will encounter types that are unique. There are many examples of this in C++, such as types like std, unique_ptr, or even a file descriptor type that owns an underlying POSIX file descriptor. These types are pervasive in languages like Rust, where copying is discouraged, but move is free. In Mojo, you can implement these kinds of moves by defining the __move_init__ method to take ownership of a unique type. For example, this is a simple wrapper around POSIX-style fcntl h functions. The consuming move constructor, __move_init__ takes ownership of an existing file descriptor, and moves its internal implementation details over to a new instance. This is because instances of file descriptor may exist at different locations, and they can be logically moved around, stealing the body of one value and moving it into another. Here is an egregious example that will invoke __move_init__ multiple times. Note how ownership of the value is transferred between various values that own it, using the postfix transfer operator, which destroys a previous binding and transfer ownership to a new constant. If you are familiar with C++, the simple way to think about the transfer operator is like std, move, but in this case, we can see that it is able to move things without resetting them to a state that can be destroyed. In C++, if your move operator failed to change the old value's fd instance, it would get closed twice. Mojo tracks the liveness of values and allows you to define custom move constructors. This is rarely needed, but extremely powerful when it is. For example, some types like the LLVM, small vector type, use the inline storage optimization technique, and they may want to be implemented with an inner pointer into their instance. This is a well-known trick to reduce pressure on the malloc memory allocator. but it means that a move operation needs custom logic to update the pointer when that happens. With Mojo, this is as simple as implementing a custom __move init ___ method. This is something that is also easy to implement in C++, though, with boilerplate in the cases where you don't need custom logic, but is difficult to implement in other popular memory-safe languages. One additional note is that while the Mojo compiler provides good predictability and control, it is also very sophisticated. It reserves the right to eliminate temporaries and the corresponding copy, move operations. If this is inappropriate for your type, you should use explicit methods like copy, instead of the dunder methods. Types that support a stealing move. One challenge with memory-safe languages is that they need to provide a predictable programming model around what the compiler is able to track. And static analysis in a compiler is inherently limited. For example, while it is possible for a compiler to understand that the two array accesses in the first example below are to different array elements, it is, in general, impossible to reason about the second example. The problem here is that there is simply no way, looking at just the function body above, to know or prove that the dynamic values of I and j are not the same. While it is possible to maintain dynamic state to track whether individual elements of the array are live, this often causes significant runtime expense, even when move transfers are not used. Which is something that Mojo and other systems programming languages are not keen to do. There are a variety of ways to deal with this, including some pretty complicated solutions that aren't always easy to learn. Mojo takes a pragmatic approach to let Mojo programmers get their job done without having to work around its type system. As seen above, it doesn't force types to be copyable, movable, or even constructible, but it does want types to express their full contract. And it wants to enable fluent design patterns that programmers expect from languages like C++. The well-known observation here is that many objects have contents that can be stolen without needing to disable their destructor. Either because they have a null state, like an optional type or nullable pointer, or because they have a null value that is efficient to create and a no-op to destroy, e.g. std. Vector can have a null pointer for its data. To support these use cases, the caret transfer operator supports arbitrary L values, and when applied to one, it invokes the stealing move constructor. This constructor must set up the new value to be in a live state, and it can mutate the old value. But it must put the old value into a state where its destructor still works. For example, if we want to put our file descriptor into a vector and move out of it, we might choose to extend it to know that -1 is a sentinel, which means that it is null. We can implement this like so. This is a simple wrapper around POSIX-style fcntl h functions. Notice how the stealing move constructor takes the file descriptor from an existing value and mutates that value so that its destructor won't do anything. This technique has trade-offs and is not the best for every type. We can see that it adds one inexpensive branch to the destructor because it has to check for the sentinel case. It is also generally considered bad form to make types like this nullable because a more general feature like an optional T type is a better way to handle this. Furthermore, we plan to implement optional T in Mojo itself, and optional needs this functionality. We also believe that the library authors understand their domain problem better than language designers do, and generally prefer to give library authors full power over that domain. As such, you can choose, but don't have to make your types participate in this behavior in an opt-in way. Copyable types. The next step up from movable types are copyable types. Copyable types are also very common, Programmers generally expect things like strings and arrays to be copyable. And every Python object reference is copyable by copying the pointer and adjusting the reference count. There are many ways to implement copyable types. One can implement reference semantic types like Python or Java, where you propagate shared pointers around. One can use immutable data structures that are easily shareable because they are never mutated once created, and one can implement deep value semantics through lazy copy on write as Swift does. Each of these approaches has different trade-offs, and Mojo takes the opinion that while we want a few common sets of collection types, we can also support a wide range of specialized ones that focus on particular use cases. In Mojo, you can do this by implementing the __copyinit___ method. Here is an example of that using a simple string in pseudocode. This simple type is a pointer to a null-terminated string data allocated with malloc, using old-school C APIs for clarity. It implements the __copyinit___, which maintains the invariant that each instance of my string owns its underlying pointer and frees it upon destruction. This implementation builds on tricks we've seen above, and implements a __moveinit___ constructor, which allows it to completely eliminate temporary copies in some common cases. You can see this behavior in this code sequence. In this case, you can see both why a copy constructor is needed. Without one, the duplication of the S1 value into S2 would be an error, because you cannot have two live instances of the same non-copyable type. The move constructor is optional but helps the assignment into S3. Without it, the compiler would invoke the copy constructor from S1, then destroy the old S1 instance. This is logically correct but introduces extra runtime overhead. Mojo destroys values eagerly, which allows it to transform copy plus destroy pairs into single move operations, which can lead to much better performance than C++ without requiring the need for pervasive micromanagement of std move. Trivial types. The most flexible types are ones that are just bags of bits. These types are trivial because they can be copied, moved, and destroyed without invoking custom code. Types like these are arguably the most common basic type that surrounds us. Things like integers and floating point values are all trivial. From a language perspective, Mojo doesn't need special support for these. It would be perfectly fine for type authors to implement these things as no-ops, and allow the inliner to just make them go away. There are two reasons that approach would be suboptimal. One is that we don't want the boilerplate of having to define a bunch of methods on trivial types, and second, we don't want the compile time overhead of generating and pushing around a bunch of function calls, only to have them inline away to nothing. Furthermore, there is an orthogonal concern, which is that many of these types are trivial in another way. They are tiny, and should be passed around in the registers of a CPU, not indirectly in memory. As such, Mojo provides a struct decorator that solves all of these problems. You can implement a type with the @register_passable, trivial decorator. And this tells Mojo that the type should be copyable and movable but that it has no user-defined logic for doing this. It also tells Mojo to prefer to pass the value in CPU registers, which can lead to efficiency benefits. To do this, decorator is due for reconsideration. Lack of custom logic copy, move, destroy logic and passability in a register are orthogonal concerns and should be split. This former logic should be subsumed into a more general @value, trivial, decorator, which is orthogonal from @register_passable. End of part 1 of this voice translation. This video could be useful for watching in the comfort of your home or by a group or individual at the office. The source of the video comes from the modular page related to Mojo. To read the remaining content, please visit https://docs.modular.com/mojo/programming-manual.html. This video was made by CesarUSA.com using Google Translate. Comments to CesarUSA.com can be sent to cusaint@gmail.com. Again, cusaint@gmail.com. We invite you to subscribe to the CUSA_INT channel, again CUSAINT. Thank you for watching. Goodbye.